I'm going to talk today about how we can learn motor skills in robotics. And for that, allow me to start with a movie clip which pretty much shows, can we adjust the darkness here since you're not going to see most of my movies. Back there, back end, can you maybe let down the curtains? Can somebody wake them up? Thank you. Let's give it a tiny second. Great start for a talk, isn't it? So, restarting one more time. Most of us computer scientists at some point got into computer science because, well, we were watching Hollywood movies, and I obviously, as somebody who did his PhD just a couple miles away from Hollywood, I have to start this talk with a movie. So what you saw in this short clip was pretty much all the things we would dream of in robotics, what future robots should have, right? But despite that Hollywood has been promising such robots since the 1920s, we are very, very far away from this, and we need to and the big open question remains for both EUCogIII as well as Pascal: how can we create such robots? And when you now look at this movie clip, what you see are three different things which should really stick out to you. The first is that there are tasks which have a lot of uncertainty in it, like these three dogs, where none of them is very predictable, and also in the environment. You will also see that you have to interact with humans, and humans are not only unpredictable, but you're actually not only unpredictable from a physical sense, but you actually can have models about them, and you would want to adapt to the humans and be safe for them. And finally, well, look at this trash can scenario. I think it's pretty hard to actually program such a thing from scratch using classical robotics, which we've been trying for a very long time. So how can we fulfill Hollywood's vision of future robotics? Well, the classical solution in robotics is very simple. It's called smart grad students. You put them in a cellar, you give them pizza, you give them Coca-Cola, and at the end of the semester, they have implemented exactly one task for you, like grab this mug. Obviously, in the next semester, you have new grad students, and you have to start a new batch of master students, and you start from square one, and you actually haven't learned a lot. So the hope would be that we get away from smart humans and hand coding, and much rather get towards the level where we can have systems that learn these tasks by themselves. Unfortunately, the promise of machine learning, of just like you take a big box, you throw data in there, and out comes the behavior which you want to have, well, this kind of no free lunch promise, this free lunch promise of machine learning has really not delivered, simply for the reason that if you just take off-the-shelf methods, it is very, very hard to scale into the domain of robotics. Instead, what we need are methods that can actually make use of all we know about skills, about motor skills, and how to acquire them for autonomous robots. So we have focused on this question of how we can find such learning systems, and we've decomposed it in three sub-questions. The first one of them is, how can we actually develop learning methods that are efficient in the context of motor control? The second one is, how we can actually use this to learn elementary behavior for anthropomorphic robots, and finally, of how we can use these behaviors in order to compose more complex skills and maybe have a real shot at bringing, well, robots into being which are similar as in the movie clip before. So let me start with the most theoretical part first. I'm going to give you an introduction into the terms of how we use them in this area of robot learning, and how we can develop learning methods that are actually sufficiently efficient to work on real robot systems. Subsequently, it's going to be more fun, and I'm going to show you loads of videos. And finally, I'm going to give you an outlook and a conclusion. So As the roboticists among you are probably quite clear, a robot is generically a system which is in a state at any point and which creates torques. I'm sorry, I can't see, I guess my laser pointer. It creates torques, which are the actions which change your environment. And finally, you have a teacher who gives a learning signal to the robot learning system. So the simplest example which is relevant would be here, where you have a very biological robot, a human who holds a racket in his hand, and on this racket there is with a string connected a ball. And he's supposed to bounce this ball. But the state is quite obviously, there is an internal state, which are all of his proprioceptive sensors, which means the angles and velocities of his arm. And this is obviously already a 14-dimensional state. Then he has the ball, which consists out of obviously a ball position and a ball velocity, which acts another 6 dimensions. And finally, you have an action, which is a torque, so it's a 7-dimensional little vector going into your system. So this is, from a machine learning perspective, actually already quite a hard problem. Now, when you take the state and the action, as we've introduced them on the previous slide, what we want to do with the learning system is, of course, learn this mapping from state to action and tell us what action to take in a certain state. We also, of course, have the teacher who evaluates the action and gives the student feedback based on how well the student has been doing. And that could, for example, be a reward R. And finally, we have the environment, which is both the body of the student as well as anything which belongs to the task, like the ball. And that, of course, is changing at every state after every action. Now, classical control engineers would have gone the way of saying, okay, my environment and body is a deterministic function, and I can write this down perfectly, and then I only have one big optimization problem for planning, and I'm all done. Now today, after robotics trying this for more than 4 decades, we know that we're not living in a perfect world, but much rather that our world should be modeled as a probability distribution, as a distribution over next states given the current state in action. So the most interesting part, of course, there is for us the part which we actually want to learn. And that basically asks the big question is how can we create these rules which tell us what action to take in what kind of a state. Classically, people, of course, try to do this as well with a deterministic function or a deterministic set of rules which tell us in every action, in every state, what actions to take. Now, who of you thinks this is the right thing to do? Oh my God, nobody. So that means you either all have seen my talk or you're way ahead of me, which is very good. So, no, stochasticity is incredibly important. Instead, we need it, first of all, for exploration. I'll give you a very simple example. When you are, let's say, a sailor, and you get into a nice sailing boat here in Mallorca, and you, for the first time, touch the steering gear of this boat, the tremor of your arm will already act as a sensitivity analysis and very quickly allow you to adapt, and you will not be doing something very stupid. So you get an amazing amount of exploration just out of this little bit of Gaussian noise, which is multiplied onto the torques in your muscles. It also, of course, eases algorithms design. So the computer scientists among you may remember Computer Science 101 algorithms, and there was something called quicksort. And that quicksort fell out of bubble sort, and bubble sort was the worst thing you could do. And quicksort was just adding a little bit of randomness and in choosing the pivot point around which you would do bubble sort, which is really a trivial way of adding stochasticity, but which turned the slowest algorithm into the fastest one, at least until bottom-up heap sort came around. It also reduces the complexity. There are quite a few problems known where the only optimal solution is actually stochastic. And in control problems, optimal control problems, you know that if you have insufficient state information and you will never be able to observe a state perfectly. In this case, your optimal solution is quite clearly stochastic. And finally, from an imitation learning perspective, stochasticity in the policy is needed to model the variance of the teacher, who is never going to show you exactly the same things. So for that reason, what we want to have is a stochastic policy, meaning a probability distribution over actions given the state, which has some parameters, theta, which allow you to do learning. And obviously, we're not just interested in one state and one action, but we're actually interested in a whole loop of them. And these we will describe in the terms of trajectories, which for us are state, action sequences. And using the terms from the previous slide, we can very nicely decompose them in this multiplicative form. We can also take the learning signals of the teacher and write them in this additive form as over there. So the big question, of course, is now, what is learning with these terms? Well, learning, of course, means that we're doing self-improvement. So what you see here is a ball on a T-ball problem. And so the ones of you who are from America may actually know this, since that's how American kids at the age of 5 to 6 learn how to hit a table tennis, a baseball ball. And it takes actually, so there's an American Association of T-ball, no kidding. And it actually takes kids on the order of 900 trials in order to hit this ball on a stick properly at the age of 5. What you see here are some outtakes where learning means maximizing the score of the teacher, and we give the robot a score if he manages to hit the ball very far, but also we give it a big punishment if it goes at very high velocities, as it may actually hurt its motors that way. And maximizing the score of the teacher is in the end what learning is all about. We're obviously interested in two types of score maximization. In the one case, we're talking about imitation learning, where we're trying to reproduce the behavior of the teacher as accurately as possible and get a score based on how close we get to the teacher's example, while when we learn just from rewards, we would only show the teacher an example and would get a score in return, which is much less informative. So with that, I think I have now given you the key terms which we need in order to get a little bit deeper into learning. The core things you need to remember is that we have a stochastic policy with some parameters which allow you to create the motor commands, and that we denote states by X and motor commands by U. Now let's focus on developing learning methods. And for that, the first thing which we need is imitation learning, reproducing what the teacher does. And this, from a learning perspective, is a very well-posed problem, because what you want to acquire is quite clearly a policy, and you have data, since you have the data of your teacher who provides the demonstration, and you can use this data since you empirically right away have a distribution over such trajectories, and all you want to do is you want to reproduce this distribution using the parameterized distribution from a couple of slides ago. So intuitively, this is a really straightforward thing to do, since what you end up having there is the distribution. What you end up having is a distribution which you've observed and one distribution which you actually generate. And the most natural way of measuring the distance between these two distributions is the Kullback-Leibler divergence. If you minimize this, something very, very nice happens, because your model is multiplicative in the same way on both sides. It actually falls out of the minimization, and you can do this one shot without actually knowing the model describing your system. And it results completely into maximizing, writes completely into minimizing this distance, which is kind of the same as maximizing the likelihood. It can be done completely based on samples without actually modeling the system, unless you have unobserved variables, in which case you would need a model of the system to fill in missing information, and in this case you would of course have to iterate. But if you have observed your complete state information, you will actually be able to learn in one shot. Roughly speaking, this corresponds to reproducing the same actions distribution in the same states as indicated in this figure over here. Reinforcement learning, meaning as much as self-improvement from rewards, is a much, much harder problem. Since when you look at it, you're again trying to learn a policy, but in this case, your teacher only gives you something very uninformative. He only gives you this score. And you are trying to produce now a very high score without actually having a notion of data in here, since you have only the distribution over paths which you generate and the rewards which you receive in return. And your teacher only tells you, well, good student, bad student. So this problem is, of course, a much harder one. Well, the whole field of reinforcement learning has been working for a very long time, very hard on this problem, but usually focused on albeit smaller scenarios which are frequently discrete in the actions and in the states, so not really that well suited for robotics. But when you look at the cost function of reinforcement learning, you realize that this is the expectation of the return where you only have the path distribution in here which you generate, but not the one which you would have observed. So quite clearly, there's something fundamentally wrong. Now you can deal with this fundamentally wrong in several different ways. A very classical way is the one you make up some heuristic which works for optimal control, and then you try to apply this to data, and obviously this you can for some discrete systems prove that this converges, but in the moment where you're dealing with a function approximation, you're losing all in continuous states and actions, as we do in robotics, you lose all forms of guarantees and advantages. An alternative is the one that you go for policy gradients, where you basically pretend your data was created by the policy which you will have in the next step, and that you only do a very, very small step in the parameter space. Of course, the first case you have frequently optimization bias, which totally kills you, while in the other case you're only doing very, very small steps which will harm your performance. So we looked into the literature on how humans actually perform, and we found this wonderful quote in actually a stochastic decision problem paper, and also in a corresponding textbook in the psychological decision literature. And that said that when humans try to create an action policy in stochastic decision problems, they don't jump to good solutions. They don't just directly jump to a good solution, overfit it if they've seen it, but much rather they do something very, very smart. They seem to, but also very weird, with puzzle psychologists for generations. And that is that they try to do a mix of the solutions they've seen, they reweight them, and then they use this reweighted previous frequencies of the actions and have this as a new policy. And that's incredibly weird, but when you think of it in the framework we have, then it makes a lot of sense. Since it basically means what they're trying to do is they're trying to match the reward-weighted previous policy with their current policy, treating the reward as if it was an improper probability distribution. So intuitively, this means something very straightforward. When you see here a distribution as we have seen in imitation learning, just in this case, we've labeled some of these data points to be good, having higher reward, others to have a low reward. Then in this case, this reward matching would boil down to just taking this distribution with a high, or staying as close as possible to the distribution with a high reward, and only when you only know bad actions, you will stay close to these bad actions for certain, well, if you only know bad actions for some of the states. So the first example where we applied this to was still during my PhD at University of Southern California, where most of the top universities in robot learning in the US were competing to teach this little dog here how to walk. When you today see some of Big Dog's videos on YouTube, which many of you have seen, many results from that project actually went into Big Dog, not necessarily what I'm showing you here right now, though. So what you see here is the dog, and it will fail and fall over because it has only 3 degrees of freedom per leg, and these are very constraining. if it accidentally dips its foot into one of the canyons between in this terrain board here, or if it steps onto one of these edges. And so the key problem becomes how to place your feet such that your posture still allows for safe traverse of this territory. And we learned this with the reward-weighted matching, where the reward was based on slip very well. But at that point, we had not fully understood it. We only learned a little bit later that this makes actually complete sense when you view it as a reward-weighted imitation learning problem, where we simply have the rewards and we reweight the path distribution, which we've observed, and we now minimize the distance to the distribution which we generate. So we can treat our past experience as if it was from a teacher. So we have a notion of data now, and reweight it and coin out the parts which work better. This allows us to treat the whole problem as if it was an imitation learning problem at every step, and at every step where we get better, we get then a new lower bound, so we're guaranteed to actually improve, at least until a local maximum in the reward. And that, of course, puts us in a different league, especially as we're dealing with robots, which we don't want to break and recable every single time. But even cooler, as you can choose your stochastic policy, you can choose your stochastic policy such that you can make it very favorable to your learning process. And one thing which you very frequently either get for free or which you can generate very fast is stochasticity in a form of Gaussian noise added to your actions. In some robots, like the DLR lightweight arms, you even get this for free because you can measure the torques which you have applied, but you also have a desired torque, and usually the difference is Gaussian noise. And also in humans, we of course have multiplicative Gaussian noise on top of our muscles, which has a very similar function. What it boils down to, what falls out of it, is what is actually amazing. Because what you get here is that we get the new policy parameters by simply taking the actions, reweighting them with the rewards, and projecting them onto the features of our policies. So that means we have reduced the whole problem of reinforcement learning onto a much, much simpler problem of reward-weighted regression. And what we can do now is that we can take our most favorite form of a regression method, and with this, create a policy and create the update rule, and directly get a very straightforward, a very stable, a very, very powerful learning process. And for us, that was, of course, really amazing, since it allowed us to now go to the general machine learning community and drag in the best methods possible. And these were 4 of the approaches which we came up with, resulting from this scenario. Now, I hope I've made the case to you guys by now that we know how to learn by both imitation learning and reinforcement learning quite efficiently, even in high-dimensional state action spaces. Now I need to convince you that this actually can be applied properly to robots. And for that, we focus on 3 questions. The first one is how we can learn elementary behavior, or motor primitives. The second one is how can we adjust these primitives. And the third one is how we can learn on a system which was previously unknown to us. So for that, I quickly want to show you a little bit of prior knowledge which we give to our learning system. Since we believe that a robot learning system should try to decompose its task into several motor primitives, and it should have, but in these primitives, store desired behaviors or can be considered sub-policies. We also have a supervisory policies, which create context actions. And these context actions can be things like parameterizing the local policy further, a sub-policy further, or activate a sub-policy. And then finally, the actions of the system are, of course, supported by a lower level system which helps you in execution. When you think it from a neuroscientist point of view, many people think that this execution module sits in the cerebellum, that this context activation, at least of tasks, could be done by the basal ganglia, and the primitives for example, could sit in the sensory motor and the motor cortex. Now, how can we learn such elementary behaviors? Well, we humans seem to rely there on motor primitives. And these motor primitives have very favorable properties, which we've been very lucky at reproducing in the context of robotics. So they are invariant under certain task parameters. They're usually very robust. We can sometimes superimpose them to create more complex primitives. So that there's and we can, of course, sequence them and do many nice things. The approach which we have chosen is that we use the dynamical systems motor primitive representation suggested by Auke Eisbert, Stefan Schaal, and well, we have also done some of the pioneering work there. We initialize it by imitation learning, and we subsequently self-improve it by trial and error with the reinforcement learning. For that, I first want to give you a feel of what these primitives mean, and no, please don't go through these equations in detail, but just notice two things. These equations have two types of parameters. On the top, you see that there are these parameters in blue, outlined in blue. These are task parameters. They allow us to adapt the behavior to a new situation. While the ones in red, these are policy parameters which allow us to learn a certain shape of movement. So when you would be thinking about, let's say, playing tennis, the shape parameters would tell you this is a forehand, this is a backhand, this is a smash, and maybe different kinds of forehands and backhands and smashes. While the task parameters would tell you, the ball is coming in at this and this, in this way, and they also hence react in such and such a way. So how can we learn such a primitive? Well, obviously by imitation learning, if we just want to reproduce behavior. And for that, the teacher shows a certain state-action distribution, and we try to reproduce it. Now, what you're seeing here is how Katharina Mülling takes the robot by the hand, and this is the robot where it has a ball on a string scenario, and that's why it's so fast. And she bounces this ball and brings it into a stable limit cycle and keeps it subsequently in this limit cycle. Subsequently, you see how the robot manages to reproduce this by just imitation learning. Now, we, of course, are both, in my group, we have both roboticists and machine learning researchers, and I've really grown up in both communities. And my student, Jens Kober, who came from Stuttgart University, which is probably Germany's best control engineering school, and he basically told me, hey, I don't believe in this learning crap. I will try to do everything with the classical control engineering, and I'll show you that this works much, much better. So before he even started this project, he spent 3 months on modeling everything perfectly by hand, creating analytical models of everything which looked so perfect that we were all convinced that an optimal control approach would work out of the box. In simulation, it seemed to work out of the box, and on the real robot, it looked really, really ugly. Then I finally persuaded him, come on, now let's start some imitation learning. And this experiment actually took us not 3 months, but basically 1 afternoon. So it gives you a little bit of a feel of how powerful imitation learning is. Unfortunately, for imitation learning, despite of being very powerful, is never enough. Otherwise, it would be very easy for all of us. I mean, we could all go to primary school and go out of primary school with a PhD and start our life. Instead, we need these painful years of self-improvement in high school, university, and during our PhDs. And that kind of self-improvement, well, we model by reinforcement learning, meaning is that we try to reproduce the good actions more frequently in our framework. Now here, you first see that we nevertheless, by starting out with an imitation, we can limit the search space sufficiently that we can actually do efficient reinforcement learning. And you see again how we, in this case, have demonstrated a ball in a cup movement. And the robot, in this case, fails to reproduce this movement. Well, why is this? Because, well, the obvious reason is a human being can produce very, very high accelerations. So it's relatively easy to jerk the ball into the cup. Robots, on the other hand, need to create a desired torque. And this desired torque cannot produce the spikes needed in order to create this jerking movement that nicely. And what you see instead is how the robot improves in step-by-step fashion, and after about 40-something trials, usually around 40, 45, 48 trials, it gets the ball into the cup for the very first time. And after about 90 trials, it gets it into the cup all the time. All of the time. 100% unless you do something evil to it. Yes, it's much better than humans. So we presented this at NIPS, which is the flagship conference of machine learning. And my student Jens Kober gave a talk there. And then after the talk, he came to me and he said, NIPS is right before Christmas. He said to me, I'm going home for Christmas and I have lots of cousins. And I gave him a blank stare, like you all give me a blank stare right now. And it turned out that he really has an extended family. And he had videotaped all of his cousins using chocolate as reward. And he could show that on this very biased sample of his cousins, the 6 to 8-year-olds never managed to learn the task at all. I think simply because they still had too much noise in their hand-eye coordination. The 10 to 12-year-olds, they managed to learn it within 30, 35 trials, so they were considerably faster already, but in the same order of magnitude as we are. And grown-ups managed to learn it within 3 trials. The only exception was me. It took me 3 months. So self-improvement is important. Now I've shown you how we can learn shape parameters. So if we always expect the same kind of things to happen to us, we can deal with having a primitive movement for that particular task. Now obviously, you don't want to learn primitive movement for every single task in the universe, since then we are back in the same problem which classical artificial intelligence hit back in the 1970s, when people finally realized they're not going to be able to enumerate all possible types of chair, so it will become incredibly hard to create the library of all chairs. For us, then creating the library of all movements would be a similarly hard problem. So instead, what we need to be able to do is to adjust our movement to new situations. Well, how would we do this? Well, for that we have these task or hyperparameters. And using these tasks or hyperparameters, we can take a movement and readjust it to a different situation. The first thing where we did this was darts. And we've actually done it on several robots, both the robots where you can control the release timing with a hand, as well as the ones where you have a dart on a sled. And the key part there is that you first learn a primitive. You learn this primitive by both imitation and reinforcement learning. And dart throwing is actually very, very hard to learn because you have to create extremely high accelerations. And it's not easy at all for a robot to create this acceleration. So we broke our robot many times that way. And subsequently, you adjust these throwing movements to the new situations of the new location on the new target, get over here, indicated by that yellow dot. And you can use the same primitive to play a game of darts, which for the English among you may be well known. This is an around-the-clock dart game, which we have there. I believe most continental Europeans don't play dart games so frequently. Correct me if I'm wrong. So, oops, I don't know why that happened. And on the right side, you see how the Sarkos humanoid CBI, which our collaborators at ATR have, how we managed to learn together with Aaron Ostap at ATR exactly these kind of dart games by reusing a motor primitive in this form. With the CBI, you have the advantage that you can release the dart because it has very lightweight hands, but it creates its torque by using hydraulics, which allows you to create very, very high forces, and which has been very favorable for us. You can even have 2 robots learn on the same reward, and here you see a throwing and a catching primitive, where initially the robot throws somewhere, and the catching guy actually doesn't know that he is supposed to catch. He only knows he has to move to the ball somehow. If you give them a shared reward of, well, you both get a reward. If one throws the ball such that the other one can catches it, they very, very quickly converge to a wonderful combination of a catching and a throwing motor primitive. So with that, I hope I've made the case to you that we know how to learn primitives and how to reuse primitives for new situations. A different problem, which I only want to glance over, since initially I was told I should talk for 1.5 hours, and I'm supposed to talk 1 hour. So I will do this very fast. It's a relatively complicated problem. That is how we can execute on an unknown system. And for that, we realize one thing which in robotics is a little bit underappreciated, and that is that our models in robotics are actually not as good as we pretend they are. In fact, when you're doing very high-speed movement or when you're trying to be very compliant, the only way of how you can do this is by having extremely good sensing, like as in the DLR arms, or by, if you want to be very compliant, or by creating models which are much better than what physics gives us. So for that, we hence need to learn how we can control accurately, and for that we need to update our model, or more precisely, use machine learning methods in order to learn better models. And what you see here on the left is the best model which the manufacturer of our robot could provide if you put it in a low-gain mode, while the manufacturer, of course, runs this when the robot is in constant co-contraction, so he's constantly stiffening its muscles, while when you make it a little bit more smoother, it will drop and it will not be able to execute as accurately. If you use machine learning methods, on the other hand, you end up having a much higher tracking performance. And let me just glance over this. We can, of course, not only learn this for movements in the joint space, but also learn this for movements in the task space. So on the upper part, you see a task space where the task space is moving a glass of water along a figure-8 primitive and keep the glass at the same time upright. On the lower one, you see a primitive which tells the robot to be at an upright position despite these pretty harsh perturbations. Learning such control laws is actually surprisingly hard, for the simple reason that when you look at these control laws, and they're basically mapping from these execution control laws, they're mapping from the output of the motor primitive represented in task space by a reference acceleration and a joint position and a joint velocity, and you map this to torques. You cannot do this just straight away by supervised learning, because you get such a totally crazy behavior for even the most simple redundant robot we can come up with, where you can accidentally track once in a while, but do not exhibit coherent behavior. So how can we solve this, or why is this so hard? Well, it's so hard because we are mapping over a data cloud which is not convex. And quite clearly, you cannot easily learn such a mapping. There are two solutions to that. One is known in the inverse kinematics learning literature, for example, by removing data from your data set or very biasedly creating data. The alternative is that you use a reward and you try to maximize this reward using the reward-weighted regression, just as if it was an immediate reward reinforcement learning problem. And when you take the same data set, you just iterate on the same data set, you get a perfect controller, which in simulation does just as good as the one you can compute off the shelf. You can compute the simulator perfectly by hand. And this even works for the real robot. So here we first have a simulated figure-8 where you see the end effector indicated by the red ball, which we will take off in a moment, and you see that you can also track this kind of a visual target using this learned operational space controller. So, and we can do loads of other things in there, including superposition, and in order to do this execution module. Anyways, so I hope I've by now made the case to you that we know how to do imitation learning, we know how to do reinforcement learning, and that we know how to learn primitive behaviors, and both by imitation and reinforcement learning, and how to adjust them to different new situations, as well as how to execute execute such primitives on pretty arbitrary robot systems, even if we don't know the dynamics beforehand, or if we have only been given a bad model by the manufacturer. So the big question, of course, is, well, can we do something more complex with this? Can we actually compose a complex skill using these elementary components? And for that, we now need all of these elementary components, which includes, well, the context policy, which activates primitives and reparameterizes them, the execution component, which allows us to control them on our body, and all of these primitives together. So let's put them all together, and let's use this in the context of robot table tennis. And we, of course, take a very training-like approach. We have first a teacher who takes the robot by the hand, shows him several primitives, subsequently does self-improvements on the primitives as well as on different repetitive targets, and finally even plays against an opponent. Now here, we are first showing you how we can teach the robot again a couple of primitives. And in this video, we're only showing forehands, but we actually have forehands, backhands, smashes, and middle positions. We take primitives, like if you were just playing to the forehand side, you would only take about 25 primitives, which for playing when you're nailed to the ceiling is actually quite a low number. And what you will see in a moment is that we can use these primitives based on in the context, and from this, learn how, by reweighting them, learn completely new primitives even in the middle, and actually achieve by imitation learning already quite a high performance at playing table tennis, in this case against a ball gun. Now, we clearly, of course, have limitations there because we cannot reproduce all of the accelerations of the teacher. We are also a robot nailed to the ceiling. If you try to play table tennis while sitting on a chair, you will see how hard this is. Hence, we need more primitives than a human being does who can sidestep, and if he stands a meter to the left, can of course play much better if you can do the sidestepping primitive instead of having to stay at one location. But let's say we stay over this and we try to do reinforcement learning. We can now very nicely pick a region where we are hitting 0% of the balls initially, because we always hit them in the net, and by doing self-improvement against an opponent who's relatively repetitive, meaning the ball gun in this case, we can become better and better, and after a certain amount of time, we will be able to return the balls properly with a pretty high success rate of about 78% in that region, where before we had 0% success. Finally, what you see here is how the creator of this mixture of motor primitives for our table tennis system, Katharina Milling, how she plays against the robot. And what you see is that the robot has become about as good as his teacher. Admittedly, she's a computer science student, and we have big hopes when our director, who in his youth was a table tennis champion, will give us a new set of primitives. But seeing him play against it already looks much more amazing than a computer scientist. But you need to stay tuned for that video in one of the next talks. He has to we first have to videotape him when he sees back from a sabbatical. So this is the current gameplay. Obviously, we have several major problems at this point. One you may have guessed already, and that is that our workspace is quite limited. A human being can sidestep simply by stepping once to the side, needs substantially fewer primitives in the close proximity of his body. The second one is that our human arm has muscles. And if you release a muscle, you have a catapult. And this catapult gives you a gigantic acceleration. That's something we don't have when we have motors. So quite clearly, we have an acceleration problem too. And finally, we have one problem which we share with the human being, but which we haven't considered in the parts of the talk before. And that is that our reaction time is actually quite short. Since when you can really only predict from the ball's flight where exactly the ball will be going after it has hit the table, because if the ball has only the minimum amount of spin, of and you get the spin axis wrong by just 5 degrees, you will actually can have an angle change of about 90 degrees. Now that's stunning when you look at one of the table tennis champions who quite clearly can deal with much, much more spin than we would ever want to do in a minimal spin scenario. And they, we know, are also very limited, A, by their reaction time, since a human being, by their central nervous system, since a human being actually only has a delay of about 80 milliseconds of just the signal going to the arm. And then you have to add another 100 milliseconds for visual processing, and you're suddenly already at 180 milliseconds, where the ball easily travels 3 meters. So the first two problems we believe we can address by taking a different kind of robot arms, the robot arm called BioRob, manufactured by a robot company, a small SME in Germany under the same name, and this robot has muscles. And these muscles are basically springs and dampers, and you can release them in a catapult-like fashion. What you see here is a simulation of such a BioRob mounted on a mobile platform or a mobile base, which would allow us now to cope with the first two of these problems, and which we hope to address in the foreseeable future. Problem number 3 is somewhat harder for us. It's somewhat harder because you cannot say, oh, we just need a good hardware engineer who helps us with muscles and a floating base, but much rather we need to deal with this more intelligently, just like humans quite clearly solve this by intelligence and not by hardware. There, we actually have made it work. So what you see here is, again, a baseball video, and this is the point when the last motor command is actually generated for your arm. So and when you talk to these players, when you talk to these baseball players, they will tell you, oh, well, we long have seen the ball arriving in our eye before we initiate our movement. That means their brain has actually simulated for them what will happen. And our idea is now that we model this and that we try to infer from the opponent in its movements how he is going to shoot this ball. And what you see here is now my student Jikun Wang, who is playing as an opponent to the robot. And these different times indicate different times before Jikun will hit the ball. So the first one is 320 milliseconds before he will hit the ball. It's relatively slow at that time at the end of the trajectory of the ball. But we are trying to predict now where he will shoot the ball to the robot. And you see that 320 milliseconds, we can maybe, you see a little peak in the middle, but we wouldn't trust it. It could as well be a forehand or some form of a middle position. But after 160 milliseconds before he hits the ball, we can already predict pretty precisely where he wants to shoot the ball. And 80 milliseconds before he hits the ball, we finally have actually a major advantage. So this gives us not just the 80 milliseconds until he hits the ball, but also the additional time until the ball hits the table in front of our robot. So it gives us a giant temporal advantage. And obviously we showed this to professional table tennis players, and they told us, duh, we could have told you this, guys. We're trained not to look at the ball, we're trained to look at the opponent. And so any professional ping pong player will try to avoid looking at the ball because it will actually distract him, and since there are too many open locations where he can shoot it. And this opponent knowledge is quite crucial, and especially in order to do this decision between forehand, backhand, and smashes, middle positions, and so on. Just to give you a feeling of the accuracy of this method is that we get you see two different methods which we used for predicting this, and both of them about 80 milliseconds before the opponent shoots the ball, it hits the ball. We already get an accuracy of 30-something centimeters where he wants to hit it. And that is, of course, outstandingly accurate and a real big advantage for the robot. And that was just published this year, and it's just in press to be published this year by HRR. So with that, I hope I've made the case for you that we can learn pretty amazing things using machine learning if applied properly in the context of robotics by both imitation and motor skill learning, by putting in just the amount of knowledge on motor skills which we need in order to start learning. And this is really our, well, current frontier, since both of the skill learning player as well as the opponent prediction player were published just this year, or will be published just this year. Now, I don't know what this remote does to me. Now I want to give you a quick outlook and a conclusion. Obviously, we're not just about table tennis. We very much plan to bring this in very different contexts, for example, industrial production, where our friends at Bosch have told us that if they could produce something at a cost where programming cost would drop substantially, this would make a huge difference to them. Since at the moment, they can only produce something with a robot factory in Germany if it at least costs 50 euros and is produced at least 10,000 times. That's, of course, a major bottleneck, but if you could take the robot by the hand and show him the task, then do some self-improvement, you may actually get this down to a much lower amount, creating new jobs and future possibilities. And these future possibilities, of course, may also be in assistive robotics, like in a hospital or rehabilitation institute. We work a little bit on rehabilitation robotics as well there already, where nurses need to program the robot. Or, well, at some point, we all want to have a robot at home, just like in the movie at the very start of this talk. So with that, I want to say, well, I've shown you mainly of how we do this in robot skill learning, but obviously, we are really at the border of machine learning. We publish at NIPS, we really focus on the machine learning community, but we also focused very much on the robotics community, and publish at all of the robotics conferences. And we also, of course, we are very interested in how it works and how motor control works in humans, and how we can apply it, for example, in the context of neurorehabilitation. So let me quickly flash some projects at you. So in the context of robotics, we're very interested in grasping, manipulation, control, but also in how we can take sensory signals from tactile interaction with our environment and make sense of these, since this is really a machine learning problem by nature. And well, we are very interested, of course, in machine learning, where we develop methods which we publish in the core machine learning conferences. And finally, well, we are interested in creating BCIs and rehabilitation in devices that can be used in hospitals, using machine learning methods and robotics, robot learning approaches, for example, adapting to the pace of somebody being rehabilitated for a stroke. We are also interested in how, of course, humans play table tennis and understand how humans' movements work, as well as computational models for motor control and learning. Now, I want to highlight support, especially from one EU project, given that we are here at the EUCogIII Pascal complex meeting. So the complex has really been very helpful for developing algorithms for us, which really brings some of the best machine learning groups in Europe together, including John Shaw Taylor and EYT and David Silver from UCL, the people from INRI around Remy Munoz and Mohamed Ghamzaveh, the inventor of the Q-learning algorithm, one of the most famous algorithms in reinforcement learning, Chris Watkins, and Manfred Opper from TU Berlin, as well as Bert Kappen from Nijmegen. And they really now help us to span the complete space of machine learning methods and see whether we haven't actually overlooked something, which could give us another factor of 5 or 10 and put us finally in the range where we outperform humans and substantially also in learning speed and not just at final performance. The other credit I want to give is to Pascal II, which has, with a thematic program of cognitive architectures and robotics, helped us substantially to organize quite a few important workshops. And I believe as we're here on a Pascal II/EUCogIII meeting, it's really worth highlighting this Pascal II program. With that, I would like to thank you for your attention and just point you to my students and postdocs who've been doing much of this work. The first two, Jens Kober and Dui Nguyen Tuong, graduated, and you've seen, for example, their work on learning single primitives for Jens and for the work of Dui for execution. And I would just like to highlight Jens for his work won just 2 or 3 weeks ago the George Gerald Award for the best European robotics PhD thesis. With that, I would like to thank you for your attention and hope you have lots of questions.